outstanding prognosis for physics in this century. I'm going to briefly talk about these topics. First, this is a century for technological revolutions, but what about physics? Are we going to have a revolution in physics that's comparable to the tech revolutions? I think we will. And to see that, we need to take a quick look at the growth of civilizations. How does technology interplay with civilization? And what is the potential then for taking civilization beyond Earth into the rest of the solar system? I can understand skepticism about this. And there are challenges about expanding into space. And so I want to deconstruct that, take a quick look at why we find it hard to believe that civilization is going to go beyond this planet in this century, and why I think the outlook is great. And finally, why I think this is going to usher in the golden age of physics. I don't think it has happened yet. I think it's about to begin. And what does that tell us about teaching physics today? So first, a century for tech revolutions. Looking at this as a physicist, we start with the simplest model, and we would say the growth of technology should be proportional to the amount of technology we already have. And so the time derivative of our technology should be some constant times the amount of technology. It's a first order differential equation, the easiest one to solve, and of course the solution is the exponential function. And the simplest model predicts that technology ought to grow exponentially fast. And surprisingly, or beautifully, as is often the case in physics, the simplest model is correct. There are many measures of technological growth. For example, Moore's law, which says that the number of transistors on an integrated circuit roughly doubles about every 18 months or so. I went through Wikipedia and I looked at all the articles on microprocessors, and I grabbed the speed of the microprocessor and the year that it was introduced, and every dot is a Wikipedia article. And on a semi-log plot, sure enough, it's exponential. And you see this not only in computers, but we see it in the speed or the accuracy of atomic clocks. We see it in the cost to do genetic sequencing. In so many areas, it's exponential growth. And so Ray Kurzweil has done a survey of 15 different lists of of all the great paradigm shifts in human history. He got lists from Carl Sagan, from organizations like Encyclopedia Britannica, and he took a look at the time between great paradigm shifts plotted versus how far in the past it was, and showed that the difference between these great paradigm shifts is getting shorter and shorter. And this is the slope of -1 on a log-log plot, so again, it shows an exponential increase in the speed of technology growth. Now, Kurzweil is famous for predicting what he calls, and what others have called, the singularity. They say this is going to happen in this century, somewhere in the middle of the century perhaps. And I think among people that talk about it, there's pretty broad consensus that somewhere in the next 100 years, there will be some event. Maybe you could define it this way. It's the point where it's not just your grandmother can't program the VCR, but nobody can program the VCR because it's just changing too fast. I help my mother with her computer all the time, but now I'm already asking my preteen daughters to help me with the social networks. And pretty soon, they're not going to be able to keep up either. So you could define it other ways as well, but pretty broadly, there is consensus that we are seeing tech revolutions that are going faster and faster at a pace we can hardly keep up with. Networking in computers, since the 1990s, the internet has exploded, and now we're about to see people wearing Google Glass, where everywhere you go, you're being fed information about what you're looking at. Artificial intelligence is exploding. Robots are being able to learn heuristically by things that they see. Google's self-driving car is a robot that you ride in. And I just read an article that says by 2025, there will be fully automated cars on the highways, and by 2050, there will be no more human-driven cars. Google just purchased 8 robotics companies, including Boston Dynamics, which is a pretty well-known robotics company. They're making a large play in that field because they believe it's the next big thing. Bill Gates wrote in a Science article just a few years ago that robotics today is where personal computing was in 1980. Robotics, manufacturing, the 3D printing craze is taking off. My lab has 5 3D printers in it, and they're going all the time. because we found we can do physics and engineering much more effectively when you just hit the print button and then you go to the printer and pick up your part and put the experiment together and run it, and then run the new version of the experiment tomorrow. And biomedical, gene sequencing, I've mentioned, the influx, a huge influx of information about our molecules in our body is leading to new ways to treat disease, and people are predicting new ways to re-engineer the dynamics of our body. But what about physics? Are we going to experience a tremendous explosion, not just continual growth, not just linear progress in physics like we tend to hope for, but are we going to have an explosion of advances in physics that keeps up with the tech revolution? Some people have said that the biggest problems in physics are mostly solved and there are only a few big outstanding questions left. I actually read a Scientific American article about that. It's been a few decades ago now. But they were saying there are only 2 big questions left to solve. I was blown away because I could immediately think of at least 2 more really big questions. But physics is the field of science that deals with the really big and the really small, as well as everything in between. And it takes a lot of money to study the very small. It takes a lot of energy, and the very big takes a lot of money too. Are we going to be able to keep pushing on at an explosive rate in physics? I think we will. But to get to that conclusion, we need to take a look at the growth of civilizations. Tech revolutions can produce socioeconomic revolutions, and I believe we're on the verge of one. Now, the Russian astrophysicist Kardashev was looking for signals of aliens in outer space, and he wisely pointed out that we shouldn't assume that aliens are going to be at the same technological level as we are, and therefore their signals might look differently than our own. And so he tried to help us stretch our thinking beyond the status quo, and he defined 3 different levels of civilization. He said a type 1 would be a civilization that uses all the energy of a single planet. Now, I think we're about as close to a type 1 as we're ever going to be. We have a global civilization. We've built it on non-renewable resources. We're being stressed, trying to find a place that's sustainable, trying to replace non-renewables. Carl Sagan tried to make Kardashev's scale more precise, and he defined it logarithmically. And according to Carl Sagan, we're a type 0.7. I think it's 0.72. But I don't think we're going to get much beyond that unless we can get beyond a single planet because issues with sustainability. Kardashev defined a type 2 as one that uses the energy of an entire star. That's 9 or 11 orders of magnitude beyond where we are today. And a type 3 would be one that uses the energy of an entire galaxy. Now, that may seem very fantastical, and why would we even talk about something so crazy, right? But to see that it's really not crazy, let's take a look at where we humans have already been. I believe we've already made several of these fantastical leaps, and it just seems so commonplace to us now that we don't realize how amazing it actually is. So let's go backwards. I'd like to define a type 0 as a civilization that fills out an entire continent. And the oceans would be the boundary of that kind of a civilization, just like space is the boundary of our civilization today. And so we call spaceships ships by that analogy. It's a good analogy. Going even further back, a type -1 would be a civilization that fills out a river valley network. The 4 great river valleys of the world are where civilization was born. And it came about because of the agricultural revolution. Our forebears, who were hunter-gatherers, discovered that by intensive farming with animal and human labor, they could grow a lot of cereal grains in a very small area. And this great concentration of food energy allowed them to support vastly larger populations in one place than we ever could before. And this led to the birth of arithmetic, alphabets, writing, libraries, a scholarly class. That was the beginning of civilization. And when this was discovered, they rapidly filled out the river valleys with cities, but they didn't go much beyond the silt deposits because they hadn't yet developed the infrastructure, the logistics, the network of fortresses to protect the trade routes that would be required before they could go on to a type 0 civilization. And even going further back, you might see a type -2 would be an isolated enclave prior to the agricultural revolution when people were still hunter-gatherers. So we have gone through several levels where we had filled out our world and maxed out what we were capable of. And then because of technological revolutions, the agricultural revolution, changes in administrative and the management of large empires, the Industrial Revolution, because of these changes, we've been able to surpass the limits of our world several times already. And I think that we're on the verge of surpassing our current world, which we define as a planet. It may seem fantastical, but imagine how fantastical it was for the ancient Hawaiians just a few hundred years ago when European ships showed up. Now, the Hawaiians lived on volcanic islands that had very little metal. They really had no metal ore. And this limited their industry, and they weren't able to have the type of industry that Europe had. And it was a shock when these ships from a world that was flush with metal and factories suddenly showed up at their doorstep. What a greater shock it would have been if we showed up in aircraft carriers and cargo ships. It was a heroic task for a Hawaiian to cross the Pacific to Tahiti, thousands of miles away, and yet they did it. Some people did it more than once in their life. Well, this little clicker I'm using to advance the slides, this contains materials that have crossed the ocean 4 or 5 times. The plastics came from oil that probably came from Saudi Arabia. It crossed the ocean, was refined maybe in Louisiana. The metal was mined maybe in South Africa. It was refined maybe in Japan. The materials were brought to China. Maybe the silicon chips were made in Arizona or maybe in Korea. It was assembled in China. It crossed the ocean again, and they sell it for about $15. Imagine that, 5 ocean crossings, and they sell it for $15. Well, it may seem crazy to talk about economics throughout the solar system, but it's no more crazy than what we've already done as humans. And it's hard still to imagine this. If you look at Hollywood, look at their ideas of aliens. The aliens are never more than 2 or 3 times smarter than we are, and in some way they're always fatally flawed and we can defeat them. That's because the aliens are really just a reflection of our fears, right? And it's hard to imagine what it would be like to have a civilization that goes beyond a type 1. It's really hard to imagine. But nevertheless, let's try to imagine it for a moment. Let's look at the potential for civilization beyond a single planet. Our solar system formed out of a nebula in the galaxy. It underwent a gravitational shock while passing through one of the spiral arms of the galaxy. This produced instabilities and collapse of the clouds, formation of stars. Because of collisions, the material eventually collapsed into a disk that preserved the angular momentum of the cloud. And as the star began to heat and began nucleosynthesis, it developed a big output of light with radiation pressure and a solar wind, which started to blow the lighter elements outward. Heavier elements like metals and silicates could condense to form planets inside of the frost line. But outside the frost line, which is roughly between the asteroid belt and Jupiter, is where the lighter elements like water would condense. And so the biggest planet, it seems natural that it condensed and formed just outside of the frost line. That's Jupiter. There were a lot of collisions from these accreting bodies in the solar system. Most of the solar system's planets show evidence of giant collisions. For example, the collision that formed our moon, or the crustal dichotomy of Mars, or the lack of much crustal material on Mercury, are all evidence of gigantic collisions. And the end result is that there is a massive amount of material that did not accrete, and it's between Mars and Jupiter. We call that the asteroid belt. And it seems the reason that that material did not accrete into a planet is because Jupiter, the largest planet, just outside the frost line, keeps stirring it up, putting kinetic energy into the cloud, so that collisions sometimes cause them to form larger bodies, and then the collisions are too energetic and they break apart again. We can see the result of this. Sometimes the materials accrete. They form what Dan Britt at the University of Central Florida Physics Department calls sandbars in space, these asteroids that are rubble piles. But as they get too large, because of nuclear decay and the mass of the asteroid grows like diameter cubed, but the surface area only grows like diameter squared. Eventually, because of the heat balance, they have to reach a very high temperature above the melting point of the rock. and they become liquid. And so the heavier elements like metals sink to the core, and the lighter materials like silicates float to the surface, and you get a differentiated body. And we know that some of the asteroids underwent this, some of the protoplanets in the asteroid belt, because the meteorites that fall on the Earth are of varying types. Some are pure metal, which came from the core of a differentiated body that then collided and broke apart. Others show evidence of coming from the mantle, and still others show evidence of coming from the crust of differentiated bodies. And this is really important from a resource point of view, because here on the Earth, almost all the metal is in the core where we can't get to it. But the asteroid belt contains protoplanets that broke apart, and the entire core of those worlds is in small bite-sized pieces. There's literally billions of times more metal accessible in the asteroid belt than there is in the crust of the Earth. Furthermore, the asteroid belt on the edges of the frost line is abundant in water and in carbon compounds. There's millions and billions of times more water in the outer solar system. The 4 largest moons of Jupiter alone have 1 billion times more water than the Earth. And so even further out, there's the Kuiper Belt and the Oort Cloud, where there are vast quantities of lighter elements. If you look at our solar system overall, the inner solar system was denuded in water and in carbon compounds and in metals at the crust, but these were brought back in through small body collisions. But the vast stores of those things are all further out in the solar system. And there's also billions of times more solar energy available in our solar system than what falls on the Earth. And it's all available without environmental impact. So I like to tell people, if you look at our solar system overall, we are sitting in a very wealthy place in the galaxy. And we really don't have a resource problem. What we have is an imagination problem. It's hard to imagine making a civilization that can access the rest of our solar system and bring it into the human sphere of activity. And it's understandable why it's hard to imagine this. There are a lot of challenges in expanding civilization into space. The first one, the biggest one perhaps, is Earth's gravity well. It takes a lot of firepower to get off the surface of the Earth. You need a lot of energy, and you have to expend that energy very rapidly. It takes a lot of engineering, and everything has to be just right. Until recently, there were only 3 superpowers that managed to put a space capsule into orbit. A capsule that was pressurized, that could hold a human, and then splash it down in the ocean and recover it. Those were the Soviet Union, later to become Russia. The second was the United States, and the third was the People's Republic of China. 3 superpowers. Well, just a couple of years ago, a 4th organization did it. It was a private company, SpaceX, which was funded by an internet entrepreneur. And I think that is the trend of things to come, because the reason he was able to do it, and to do it affordably, is that he used new manufacturing technologies. He uses 3D printing extensively, and he does a lot of his manufacturing in-house in order to take advantage of new techniques and to do it at a discount. And I think, well, and in addition to SpaceX, you've got many companies building lunar landers. There are several U.S. companies ready to land on the moon, and many more international companies ready to land on the moon beginning next year. And in addition to that, we have more launch vehicles under development by private companies and space tourism, which is typically suborbital at this point. I think that the gravity well problem is being somewhat mitigated. In addition to the gravity well problem, we have vast distances in space. It's a long way to go anywhere. To Mars, you're talking about 6 months or more. And during that time, you're exposed to the environment of space. The vacuum, temperature extremes, radiation, which is a really serious problem for long journeys. Zero gravity, your body is adapted to 1G. The flexure of your bones is required in order to keep bone density up. And there's a need for technical perfection. One little failure and everybody on your spacecraft could die. And there's a lack of infrastructure in space. And ultimately, to overcome these problems, there's the cost problem. And because of these, we understand space travel is hard. It's been hard up until this point. Looking at another aspect of this, here's a picture from planet Earth. Life has transformed planet Earth, starting with bacteria in the soil, and then worms, fungi, eventually plants on the continents, followed by animals. Earth has been thoroughly transformed by life. But life requires liquid water. At least abundant life, like we have here on Earth, requires liquid water at the surface where there's also abundant energy, solar energy. And as far as we know, there's nowhere else in the solar system where we can get that. And therefore, life has been, for the most part at least, limited during the past several billion years to planet Earth. And therefore, when we go to colonize somewhere on planet Earth, when the humans arrive, they find out there's already a lot there that we need. There's trees that we can use to make buildings. There's plants that we can use for clothing, and there's food. And when the Europeans showed up in North America, there were already other humans who had arrived. So he showed them how to use these resources. When we go to space, it looks more like this. The regolith has not been transformed by life. That's Mars. And there we have the moon. There we have Titan, one of the moons of Saturn. And here we have asteroid Itokawa. They have regolith. They have ice a lot of the times, or hydrated minerals, so there are volatiles. There's sunlight for energy. We don't have liquid water at the surface, and we don't have abundant biospheres to transform it, to create the food chain that we need as humans. And so we imagine space travel being like this, where we build habitats that are little isolated refuges for humanity. There's the moon, there's Mars, and there's in zero gravity. Now, Gerard K. O'Neill was responsible for these studies that were done through the 70s and through the 90s. And they, up at Princeton, they did a lot of work on what would it take to get a self-sustaining civilization in space. And he was looking at having humans living in floating spacecraft, doing manufacturing, creating power stations to beam energy down to the Earth. And by their estimates, back in the 70s through 90s, it would take 10,000 people living in one of these O'Neill cylinders in order to break even, to begin to make a profit, and therefore to get off of the congressional budget. And unfortunately, putting 10,000 people in orbit was a little bit too expensive, and so we didn't even really consider doing it, which is unfortunate. In order to get over that ignition point, during the exploration phase, you don't make a profit. It's uneconomic. You do it for science. You do it for idealistic reasons. Early colonization on Earth has always, or has often been driven by idealism. People don't typically think they're going to get a better life when they go to a primitive area. They do it for idealistic reasons, for their faith, or for building a better future in the world. And then eventually the colony reaches the ignition point where you get enough humans and enough infrastructure to turn a profit, and then economic growth occurs. That's a pretty high barrier to occur in space. And so it's really understandable to be skeptical to think that we might do it in this century. But here is why I would claim the outlook is actually great. Remember, we're on the verge of a robotics revolution. And if we go back over that list of the challenges of spaceflight, they apply to humans, but only one or two of them are a challenge for robots. Robots don't get bored on long space journeys. Robots can be built to handle vacuum. They can be built to handle radiation. And manufacturing is a critical thing for space industry, because if you can make everything in space, you don't need to launch it, and that solves the problem of Earth's gravity well. We just need to get a startup level of infrastructure in space, and then we can stop launching everything except the people. 3D printing is truly revolutionary. These are pictures of a few of the things that are being made today. The lower right-hand corner came from one of my collaborators, Brock Koshnivas at the University of Southern California. He's spearheading technology to print 3D houses, and we're working with Professor Koshnivas to adapt that to space. So in 1980, as early as 1980, there was a study at NASA Ames Research Center saying, look, we can solve these problems through robotics. We can put a self-replicating factory on the moon, and we can make everything, or just about everything. They were aiming for not quite full closure in the industry. You would still need to send computer chips from Earth. And they did a study to show what would it take to start up this industry. And by their estimates, you would need about 100 tons of robotics and manufacturing equipment on the moon. They fleshed it out in pretty good detail, and they left the study off by making some recommendations. One recommendation was, let's pursue these technologies, because when we get these technologies, we can actually do this. Well, the government, or NASA, didn't really have a program to pursue these technologies, but the consumer world has done it. And everything that was described in the study in 1980 has been pretty much developed already, except it needs to be adapted to the space environment still. And so looking at this, I did a study a few years ago with my colleagues where we said, let's, instead of launching a factory to the moon, let's evolve a factory in space. And let's see if we can get it down from 100 tons of hardware to something much less. And so we defined some notional levels of industry in space. We talked about in great detail the first level of industry, what it could make and what it would require to be brought from Earth to create the second level of industry. And we did computer modeling of this, and I want to admit it was very crude computer modeling. And the purpose was mainly to show people that things are possible today that weren't considered a few decades ago, so that we could get more people interested in this study. And so, admitting that it was crude modeling, let me show you the results. The modeling shows that, as expected, the industry in space can grow exponentially. And after about 6 generations of hardware, which is about 2 years per generation, we're talking about 12 years, 10 to 20 years, after that much time, we could have 60,000 tons of hardware on the moon and 100,000 robots, and that comes at the cost of launching just 60 tons. We can get that down even less. The amount of mass that we send to the moon can be reduced to as low as 12 tons, and the end result is one factory at the end of 12 years, one factory that's fully self-sustaining with 150 tons of hardware and can make everything, including the computer chips. And there's no new physics in this. This is straightforward engineering using technologies that are pretty much available today. There's a lot of physics required, applied physics required to instantiate this, to actually make it happen. But there's nothing magical required to do this. It's all pretty much straightforward. And the modeling furthermore says that after bootstrapping this industry in near-Earth space using the moon and asteroid, in just 20 more years, we could take it to the asteroid belt, where it could grow to have 1 million times the industrial output of the entire planet. And then after just 10 more years, with that exponential growth, it could be 1 billion times. And what could humanity do with 1,000 or 1 million or 1 billion times the ability to produce goods and services per capita? Well, think of it this way. The robotosphere is like the life that's missing in space. It's the ecosphere of space. Or you could look at it as making the entire solar system into a single living cell with a metabolism, moving materials around. It can beautify the solar system. I'm not thinking about industrial smokestacks. I'm thinking about life. This would be the equivalent of life in space, working under the guidance of physicists and artists and architects. When you've got 1,000 or 1 million times excess capacity to satisfy our needs, then you don't have to skimp. You don't have to do things grotesquely. We could have cities of great architectural beauty and works of art. We could terraform worlds, create colonies, and even look towards interstellar travel. My estimate, in order to accomplish this, looking at prior space programs and how much it costs for development plus implementation, this would only be about 1/3 of the cost of the International Space Station. In other words, it would be about 0.04% of the federal budget over 40 years. I think we can afford that. The benefits are almost impossible to imagine because we're talking about going to the next level of civilization. We could have global relief effort to the Earth, take dirty industries off the Earth, beam down clean energy. We could take people up to the resources, have colonies in space. That'd be the Great Migration. Or we could have the Isaac Asimov, the Foundation in space, as a minimum, just a backup to civilization. Or we could have the Space Endowment, an institute in space fully funded so that anybody who wants to study anything or do arts or literature, they can spend a portion of their life in space with all the funding they want. These are some of the ideas of what you could do if we had industry beyond planet Earth. And I think this will usher in the golden age of physics. I can't show you any pictures of what it'll be like. I'm not an artist, but I can tell you in words some of the ideas of what's possible. If we had this sort of economic power beyond the Earth, We could have gigantic particle colliders constructed in orbit somewhere near Mercury with vast solar arrays collecting energy to probe physics at energy scales that are currently unthinkable. We could have gigantic telescopes peering off into the depths of the cosmos. And all of these things could be built by our robotic industry for very little cost to the nations of planet Earth. We could have outposts on every one of the hundreds of moons and planets in our solar system. We could have shipyards building the transportation systems to take the scientists back and forth to study these worlds or to study from these worlds, to do experiments in gravitation, cosmology, planetary science. And so what does this grand vision of the possibilities for the next century tell us about how we should teach physics today? First of all, jobs for physicists. I think there are two categories of jobs indicated by this vision. First of all, there are jobs developing space industry. Second of all, there are jobs benefiting from space industry. Developing space industry is what I'm doing as a physicist. It takes physicists to understand the space environment, to adapt the robotics to that environment, to understand planetary environments, to adapt the technologies to the hundreds of worlds where we will be going, to develop new manufacturing techniques to deal with the resources in raw, crude form without the benefit of the logistics that we have here on Earth. Then there are jobs benefiting from the space industry. We will have enhanced opportunity for science in space, as I've just described. Outposts, observatories, spacecraft carrying out missions. Right now, we have so much trouble getting funding for these missions. Think what a great world it's going to be for physics when these spacecraft are being built in space at very little cost to the Earth. And then there's going to be a flood of data from space, big data, data that requires analysis, data that's going to allow us to peer into every corner of physics, of cosmology, planetary science, and every other realm. To give you an illustration of physics in this area of work, let me tell you a little bit about the lab that I work in. I'm part of the Kennedy Space Center SwampWorks. The SwampWorks has about 10 physicists, about 10 chemists, about 10 biologists, and about 10 mechanical and aerospace engineers. It consists of 4 labs. The Granular Mechanics and Regulative Operations Lab is the one that I co-founded and manage. We have about 5 physicists and about 10 engineers in that lab. It's a great mix. There's also the Electrostatics and Surface Physics Lab, which are physicists, the Applied Chemistry Lab, which of course are the chemists, and the Sustainable Life Support Systems Lab, where the biologists reside. In addition to my lab, there are these private companies, and there are a number of companies that are developing technologies to mine in space. It's a growing list, and we're collaborating with these companies. Every one of these companies, we've had contact with them or contracts with them or Space Act agreements. I've added SpaceX to the list, although they're not primarily a mining company. I'm projecting they're going to need mining in order to do colonization on Mars, which is their objective. And we have had meetings with SpaceX, and we're collaborating with them to develop these technologies to use space resources. Some of the things we've been doing. A few years ago, we went to Mauna Kea in Hawaii, where we were developing technologies to extract oxygen from the soil. We went to Mauna Kea because the volcanic ash is a pretty good analog to lunar soil. It's above the tree line in Hawaii, and therefore it's an area that's been relatively unaffected by life. And we had robots that were from Canada scooping up the ash, dropping it into a unit that my lab built with a company, Honeybee Robotics. And this unit transferred the soil into a chemical reactor, which was built by another small company in collaboration with the Applied Chem Lab in the SwampWorks, using solar concentrators that the Sustainable Life Systems Lab developed originally for plant growth, but we've repurposed it to melting lunar soil. And we did the chemistry and extracted oxygen from the soil, and we used the oxygen to fire a rocket. And so it went from volcanic dust to rocket thrust. We called it dust to thrust. And it all worked. We were able to show that you can get oxygen from a rock. The moon, by the way, is about 42% oxygen by weight. The sand out here at Cocoa Beach is about 50% oxygen by weight, roughly. It's because the minerals are fully oxidized. So oxygen is abundant in space. And launching oxygen off the Earth is arguably the biggest cost of spaceflight. We've tested these technologies in reduced gravity. Here's Adam Dokos and Van Townsend studying the transferring of soil in and out of chemical reactors in lunar gravity in an aircraft flying parabolic arcs. We've looked at site preparation, so if you want to build a landing pad on Mars, how do you do the grading, or on the moon or another body in space? We've developed very lightweight excavators with robotic rovers. In the foreground in this picture is Razor. The roboticists in the granular mechanics lab developed this for mining in ultra-low gravity environments. In space, you can't afford to take a gigantic earth mover. And when you get there, not only is the mass of your vehicle small, but the gravity is small. So low gravity times low mass means the weight is exceedingly low, and therefore you get very little traction on the treads to do the digging force. And so the trick that the roboticists came up with is don't rely on traction to do the digging. Dig in both directions at the same time and let all the forces cancel out. And they were able to make it work. We've shown that we can mine cryogenically frozen lunar soil with water ice, which is as hard as granite, using 1/6 of Earth's gravity weight on the treads. So it's lunar gravity weight. And it successfully was able to mine the frozen soil. My personal area of research is in how rocket exhaust blows soil. And so I've been firing rockets into sand beds, trying to understand the physics of supersonic jets, especially in rarefied flow in a planetary environment or a lunar environment, interacting with soil. And we've analyzed videos. You see the top row of pictures from the Apollo landings. And we've analyzed the blowing of the dust. We've blown rocket thrusters onto volcanoes to study the interaction of rocket exhaust with complex regolith. And we've discovered really interesting physics. There's plenty of work here. I'm going to end up being able to finish my career without ever finishing this problem because it's a really fun and really challenging problem. We've had a mechanical engineer with a with a physicist, come up with the idea of making heat shields out of dirt so that you can make Mars missions much cheaper. And they were able to show, using the ArcJet at NASA Ames Research Center, that these heat shields made of dirt are actually viable. They are very functional. They can reduce the cost of Mars missions by billions of dollars. And they might also make mining asteroids for metal economic. And there are hundreds of worlds in our solar system alone, each with unique environments that we don't understand very well. We need physicists working with engineers to develop these technologies in order to bring the solar system into the human's economic sphere. When we do, I believe that it's going to be a fantastical 21st century. I think the golden age of physics is just about to begin because civilization is just about to rise to a new level. Tech revolutions will dominate this century, but it's not just a century of technology. I think it's a century for physics because surprisingly and suddenly, it is actually becoming easy to start industry in space. And once started, space industry will take our civilization to an entirely higher level. The need for physicists and the potential for doing physics in the solar system are thus unbounded. And teaching physics and spreading the enthusiasm for physics are therefore more important than ever. Thank you for your attention. That's a great question. The question was about the international governance of space. I'll start out with the caveat that I'm not a lawyer. So there are two treaties. There's the space treaty, the Outer Space Treaty, and the Moon Treaty. So far, no spacefaring nation has signed on to the Moon Treaty. So the Outer Space Treaty is the primary one. The Outer Space Treaty forbids national ownership of property, of territory in space. Unfortunately, there aren't really strong teeth in the treaty because any country can get out of the treaty with just a 1-year notice. And because it takes many years to prepare a space mission, it really has no teeth. But for nations of goodwill, that is the governing document. There is a question: can private companies own land in space? And many people think that it's possible. And I don't want to give you an opinion, since I work for the federal government. I will just tell you what I've heard people speculating. Some people have pointed out that foreign nationals can own property in the United States, for example. That doesn't make the property they own part of their country. It's still the United States. So private ownership does not confer national territory status on property. And so they have argued that the treaty does not forbid private ownership. However, it's widely agreed that there is a lot of uncertainty about the ability to do mining. And one way that we could help humanity along to a civilization beyond one planet would be to take away that uncertainty, to create a system where there are mining rights and recognized laws, recognized rules that everybody can follow fairly. So that's where it is right now. I don't want to say any more about it since it's outside my expertise. Any other questions? Yes?
You said that there were many companies ready to land on the moon next year. Are there also companies that are ready to get to the moon next year? So is that going to be happening?
Okay, it sounds like everybody heard the question. For the camera, I will say the question was, there are many companies ready to land on the moon, but are there many companies ready to get to the moon by next year? So I know that I'm closest to only 3 of the Google Lunar X Prize companies, and I've spoken to the CEOs and the workers in several of those companies at great length, and I know that they are not developing launch vehicles, they're developing landers. And so their plan is to purchase the launch from an existing launch provider. And so there are several companies I know that fully intend to land on the moon in 2015. And as far as the international companies, I don't know as much about them. But there's a website that tracks the Google Lunar X Prize competitors, and it tells the status on what they think the leading competitors are. And there's one that's overseas that's always a top runner, and there are a couple in the United States that are always in the top running. So I think that they're going to do it. I think that there are at least 2 or 3 that are going to, I think they're going to land on the moon in 2015, private companies using almost entirely private funds. Yes? I'm sorry, I didn't hear the part of the question. Moving mass from the planets are... Yes. Okay, that's a common question. So will space mining, will moving large amounts of mass change the dynamics of the solar system? And compared to natural process, the answer is no. Every year we have, I think maybe about 80,000 tons of dust fall on the Earth from space. 80,000 tons. I think it's 40,000 tons. But we have about 80,000 tons of helium and hydrogen escape from the Earth. And so the Earth is losing weight every year. And besides that, nothing's really eternally stable in the solar system anyways. The moon is moving further and further from the Earth already. And already we have bodies that are moving chaotically. Asteroids occasionally get kicked into the inner solar system. Once in the inner solar system, they only live on the order of millions of years. And so they eventually collide with a planet. And the dynamics of the solar system, seen in that light, is kind of harmful for life on the Earth. And it would be nice if we could take control over that, if we could take control over all the small bodies. Well, there's no way that a Type 1 civilization can control the millions of small bodies in our solar system, but a type 2 civilization can. And so we could map and take control of every body in the inner solar system, the asteroid belt, and then begin working our way outward to try to make our solar system a safer place. So the answer is, we're not going to disrupt anything negatively. It's orders of magnitude less effect than what nature is already doing. But there is the potential to change things positively to help life here on the Earth. And by the way, I think we have a responsibility. It's not just about human civilization. If we don't create a type 2 civilization, every single species on planet Earth will go extinct. And their only hope is if we go beyond a single planet. So it's not just about us, it's about all the other species of life. I've said before, if you want to save the whales, we need to have spaceships for whales. So we can terraform water worlds and get the whales beyond a single planet, because sooner or later they're going to go extinct in this dynamic universe that we're in. In the back. Yes.
What are your thoughts on space elevators to help get mass and use rockets outside?
Okay, what are my thoughts on space elevators? Another great question. So the challenge with space elevators is that the materials to get out of Earth's gravity well really have to be extremely strong, extremely light. The equation for the tensile strength shows that the further up the cable you go, the fatter the cable has to become in order to support the weight of everything below it. And so by the time you get to the top of the cable, it's a really fat cable. And that means you've got to put a lot of mass up there. And the coolest idea I've heard to date is to bootstrap the cable by putting a really thin cable, one that can't really take much payload, but it can support a small climber that can then climb up and down the cable, thickening the cable with every pass. And so over time you can build the cable and get it up to that really strong mass by using the elevator itself to build the elevator. Then that leads you to the question, well, we know the environment of space degrades materials, micrometeorites, radiation damage. Can you build it faster than it will degrade? And unfortunately, the answer seems to be no. And so we're not quite sure that we could build a space elevator to get out of Earth's gravity well. There are proposals that we can do it. And it's right on the limit where it may be possible. I know a way to do it, I think. I'm not really ready to tell yet because I've been writing grant requests. And so far we don't have funding. But if you paid attention to the talk, you know I'm all into resources in space and not launching stuff. So I think you can probably guess the basic idea. Space elevators on other bodies, like the moon, very doable. You can use a simple fiber like Spectra and have a space elevator come back towards the Lagrange point towards Earth. We can do that today. Mars, it's very much more doable than on Earth. So I think that's the state of the art today where space elevators are. I would like to see these technologies go forward. Yes?
Your proposal presents a lot of raw material and energy use, but as you're well aware, there's many other problems on Earth that those who are used to solve seem to be picture for the Earth as well.
I missed the very last thing that you said.
Can you go into the environmental, food, population, for example?
Yes, okay. So besides the economics of resource materials and energy, what about the other problems we have here on planet Earth? Okay, so population. I used to be very scared about population and planet Earth. Whenever I would go to a talk, the economists would stand up to give the presentation on the economics of building a starship, for example. And their first chart would always show world population leveling off around 16 billion or something. And so after the talk, I would always ask them, well, what is the mechanism that makes that happen? Why does population level off like that? And they would say, well, as the whole world becomes economically well-to-do, like the West, there's a psychological shift that happens, and people stop having as many children. And so then I walked away from there saying, well, so the key is we've got to get everybody wealthy like we are in the West, at least to the level of Western Europe, the energy usage levels of Western Europe globally. Is there enough energy to get 16 billion people living at Western Europe's standard of living? And I was desperately afraid the answer was no. And so I was not sure if we were going to win this race to getting beyond that problem in order to get the whole world to a standard of living where we can become stable. Well, I've recently heard talks that make a pretty compelling argument that world population is already stabilizing, and we're just backfilling. All the generations that are younger are backfilling up to a limit of 10 billion. So we think that the population of the world is already becoming pretty stable. Furthermore, we've had some changes in non-renewable resources, for better or for worse. There's fracking now, and I think that's given us maybe 3 decades of extra non-renewable energy, for better or for worse. So I don't think the crunch on energy is as tight as it used to be 10 years ago. As far as social problems here on the earth, I don't work in that field, and I don't have any solutions. All I can do is offer that I think if we can get beyond a single planet, if we can get beyond the limitations that we currently have, there may be less motivation to fight over everything that we've got here on the earth. One thing that we're not going to have more of is real estate on the earth. Until we can terraform Earth-like planets, and that means until we have a lot of solar systems in our civilization, there's going to be a limitation of real estate. And so there will always be that to fight over. But I'm hoping that if we can solve the other economic problems, there may be less motivation for fighting, and there may be more hope for making a better world. That's the best answer I can give. Okay.
What you're talking about is taking an economic leap to get to type 2 civilization. And there are things that can drive such economic leaps, and I wonder what you think might drive one to get us on the track to get to a type 2 civilization.
Excellent question. What is the leap? How are we going to take this leap to get over the ignition point, to get over the activation energy of a type 2 world? And I spend most of my time outside of work, when I'm thinking about space, thinking on that exact question. So I didn't have time in my talk to go through the economics of getting over the hump, and I took some of those charts out. I've got a list on the whiteboard at work of how do you make money in space, or how do you motivate people of the earth to invest money in space. And we have about 19 things on the list. Some of the ideas are really crazy ideas, like put penal colonies in space. And I have a friend who insists that nursing homes should be in space because there's less gravity, so you won't fall and break your hip as often. But I cannot imagine a grandmother wanting to live the rest of her life on the moon when her grandkids are on the earth. I cannot imagine that. So some of the ideas I don't think are really viable. There are some viable ideas. Mining metals, it's questionable if you can do that economically. I think you can, especially because of the heat shield I talked about. There are ways that you can make it economically viable, I believe. Another big one is doing resource development to support science missions. The democratic and even the non-democratic nations of the earth have some typical science budget for doing space missions. If we can use resources of space, we can do those missions more affordably. So there is an economic driver for some limited development of resources in space right there. Geosynchronous communication satellites can be carried from low Earth orbit to geosynchronous orbit using water from the moon or from asteroids vastly more affordably than if we have to launch all the fuel from the Earth. Even that has startup costs, though. When I look at all the ways to make money in space, I'm not really completely convinced that it's enough to do it. And that's why I did the study about having the government directly fund it. What if we, as a government project, directly fund the starting of industry? And I think I showed it's very affordable, and there's no reason why we can't do it. So I think with appropriate government investment, with the participation of the commercial space companies, I do think we have more than enough potential to get over that hump. And that's why I'm very optimistic, and I do think that we're going to get over the hump in the next couple of decades. Okay, so thank you so much again.
Okay, the session is officially over, but Dr. Metzger has volunteered to stand up front and answer additional questions from anyone who would like to ask them.